Hi guys, this is Dr. G here, and in this video we are going to talk about reactions of epoxides, and most of these reactions are actually ring opening reactions for epoxide. So in this part of the video we are going to talk about a few different reactions that will be used to in order to open the epoxide ring. Okay, so the first reaction that we are going to talk about is the uh, opening epoxide ring opening using a dilute acid. Okay, in this first step or in this first reaction we are going to use a dilute acid. Okay, and that is the only thing that you need. And in this reaction you will basically obtain a diol. Okay, a diol, or you can say a 1,2 diol, which is usually a trans product, So in this reaction you are going to generate a trans 1,2 diol. So by using a dilute acid you can obtain a trans 1,2 diol. So if you ever need to generate a trans 1,2 diol, this will be the reaction that you will use. So in this reaction, by using a dilute acid, you protonate the epoxide oxygen. Okay, so the first thing that you are going to do is you're going to protonate the epoxide oxygen. Okay, once the epoxide oxygen is protonated, it resembles the bromonium ion. The protonated epoxide oxygen resembles the bromonium ion, and it invites the nucleophiles to attack one of the two carbons. It invites the nucleophilic attack on the two carbons that shares a ring with oxygens. And usually the nucleophile that you have is water. The only nucleophile you have in this medium is water, and water will attack one carbon on the opposite side. Remember, bromonium ion and this epoxide, they are both basically shielding one side of the ring. Okay, so the incoming nucleophile can only come from the opposite side. So therefore the product that you will get will always be trans. Okay, so the major product will always be a trans product. Why? Because the two OH groups will be on opposite planes of the ring. So this reaction is once again capable of generating trans 1,2 diols. So let's do a simple synthesis type reaction. So if you wanna generate a trans 1,2 diol, okay, if you want to generate a trans 1,2 diol, okay, like the one that I have given in this example, okay, clearly for this synthesis you are going to need to generate a trans 1,2 diol. So the first reaction will basically involve the preparation of an ether. So you will first generate an ether. Okay, how do you get this ether? You can use a peroxy acid. So RCO3H. Okay, and then once you have a peroxy acid, you can use a diluted acid in order to obtain a trans 1,2 diol. Very straightforward. Okay, all right. So the next reaction that we are going to talk about is the epoxide ring opening using a stronger acid. Okay, in here especially we are going to use strong acids or anhydrous strong acids like HBr, HCl, or HI, or sometimes you can also use a weaker acid like HF. Okay, so the acids that you need for this reaction are going to be HF, HCl, HBr, or HI under anhydrous conditions. So that is why we are using a ether here to provide anhydrous conditions. Okay, so this reaction is somewhat similar to the previous ring opening reaction, but the main difference is that instead of giving a diol, this will basically give you a OH group on one carbon and a halogen on the other carbon. The previous diluted acid reaction gave you a trans 1,2 diol, but in here you will get a trans product, but it is not going to be a diol. Instead, it will be an OH on one carbon and a halogen on the other carbon. Halogen on the other carbon. Once again, they will be trans to each other. They will be trans to each other. Okay, so in the next slide I have a few examples. Okay, so the regiochemistry of the reaction, okay, will basically depend on the type of ether, or sorry, the type of epoxide you have. Okay, so basically if you have an epoxide where you have a secondary carbon on one side and a primary carbon on the other side. Okay, so if you have a reaction where you have a secondary carbon on one side and a primary carbon on the other side, then of course the incoming nucleophile, which is the halide, will attack the less crowded primary carbon. If you start with a primary carbon and a secondary carbon containing epoxide ring, the incoming nucleophile will attack the less crowded primary carbon. But if your epoxide contains a tertiary carbon, if your ether contains a tertiary carbon, okay, in the epoxide ring, then the chloride ring, chloride nucleophile, the nucleophile chloride will mostly go into the tertiary carbon. It will mostly go into the tertiary carbon. Okay, it will mostly go into the tertiary carbon. Okay, mainly because tertiary carbocations are more stable. So when the ring breaks, it breaks in order to obtain a tertiary carbocation. So keep these two examples in mind. Okay, so if you don't have a tertiary carbon, usually the nucleophile will attack the less crowded carbon, but if you have a tertiary carbon, the ring will break in order to obtain a tertiary carbocation. So therefore the nucleophile will mostly be on the tertiary carbon. Okay, tertiary carbon. All right, so this basically explains it further. So if you have a tertiary carbon, which is this one right here, okay, if you have a tertiary carbon on the epoxide ring, so the epoxide ring tend to break in order to achieve a more stable tertiary carbocation. The epoxide ring tends to break in order to achieve a more stable tertiary carbocation. So the nucleophile will be present on the tertiary carbon. Okay, on the tertiary carbon. So that is something that you might want to remember. All right, here is a worked example. So see if you could do it without my help. So pause the video and try this, and then we will do it together. Okay. All right. So the compound that you have here has an epoxide ring, and then you are using a strong acid in anhydrous medium. Okay. So basically, let's first worry about the carbons that are present in the epoxide. So you have a tertiary carbon and a secondary carbon. Okay, so you have a tertiary carbon and a secondary carbon. So when you have a tertiary carbon, we just learned that it tend to break in the direction where you can achieve a more stable tertiary carbocation, right? So the nucleophile will be present, or the incoming nucleophile will attach on the tertiary carbon, will attach on the tertiary carbon, will attach on the tertiary carbon, giving you this product. Okay, so this is the product that you will get. This is the product that you will get. All right, so let's double check your answer. Okay, the solution once again is this: the major product will have the nucleophile on the tertiary carbon, and the OH group on the secondary carbon. OH group on the secondary carbon. All right. So let's do another example. Let's try another example. Let's do this. So let's have an epoxide. Here is our epoxide. Okay. So this is the epoxide that we are looking for. Okay, let me draw it a little bit better. Okay, so here is your epoxide, and maybe I will remove this carbon. Okay, so this is the epoxide that we have, and then let's say you are treating it with HBr, in the anhydrous medium. So let's have an ether. So what will be the expected product? So to get the product, what you need is the type of carbon that you have. This carbon right here is a primary carbon. This carbon right here is a secondary carbon. So you have a primary carbon and a secondary carbon. In that case, the bromide, the nucleophile bromide tend to attack the less crowded carbon. It tends to attack the less crowded carbon, giving you a product like this. The secondary carbon will have the OH group, and the primary carbon will get the nucleophile bromide. Okay, so this will be the product. Okay, so whenever you are predicting products, always make sure to categorize the carbons that you have attached to the epoxide ring. Okay, that is the most important thing. All right, so the next reaction that we are going to talk about is base catalyzed epoxide ring opening. Okay, so the next reaction that we are going to talk about is the base catalyzed epoxide ring opening. Okay, so in here, of course, you are going to need a base. So in here you have a hydroxide ion. Okay, this is your base. Okay, you can actually use a strong nucleophile and then achieve the same results. Okay, so in here usually the base attacks the less crowded carbon. Okay, base attacks the less crowded carbon. So you might want to write that down. So base attacks the less crowded carbon. Okay, so the major product will always be where your OH group is attached to the less crowded carbon. Okay, OH group is attached to the less crowded carbon. But here's the thing, do you see a difference? Will you see a difference? Probably not. Why? Because I mean both carbons will get an OH. Okay, will get an OH. So in here, even if you don't know where the OH is going to attack, it doesn't make any difference. Why? Because both carbons, okay, so here is one carbon, here is the other carbon, both carbons will at the end get what? Get an OH. So it wouldn't really matter. Okay, at least for the purpose of predicting products, it wouldn't really matter where the OH minus group is going to attack. Okay, but anyway, so this is the product. Once again, you will get a diol. In this reaction, you will get a diol. Okay, you will get a diol. So the next reaction that we are going to talk about is a very important reaction, especially it involves the Grignard reagent. Okay, it involves the Grignard reagents. For the people who does not remember what Grignard reagent is, Grignard reagent basically has an R minus an ion coupled to a magnesium halide cation. Okay, so this is the general formula for Grignard reagent. Okay, so you have a alkyl group, okay, R minus anion attached to a magnesium cation. Okay, so this reaction is especially important. Why? Because you can increase the number of carbons in this. By using this reaction, you can increase the number of carbons. Whenever a reaction is capable of increasing the number of carbons, that reaction is very important in organic chemistry. Why? Because most of the times in organic synthesis reactions, we start with very simple small organic compounds, and then at the end of the day, we want to make something with more carbons and more functional groups, right? So therefore, the reactions that adds carbon are very important. Okay, the reactions that add carbons are very important in organic chemistry, and in this reaction you can easily add carbons. Okay, so this R group right here in the Grignard will be the new carbons that will be added to the added to the epoxide. Okay, added to the epoxide. So in here what I have is butyl magnesium bromide. Okay, so I have a magnesium bromide salt with a butyl group as the R group. Okay, and then it will attack the ethylene oxide, okay, which is a 2-carbon epoxide. And for the product, you will get an alcohol. The product will be an alcohol, and it will have an increased number of carbons. It will have a greater number of carbons. It will have a greater number of carbons. So let's try this one. Let's see if you could do this worked example without my help. Okay, so pause the video now and then see if you could do this one. All right, so in this example, what we have is an epoxide. Okay, it kind of looks like this. This is the epoxide that we have, and of course in here you have a secondary carbon and a primary carbon. It seems like it is not very clear in this writing, so let me just use regular red ink. Okay, so this is the epoxide that you have. Okay, on one side you have a ethyl group and a methyl group, sorry. Okay, and then one side of the ring has a primary carbon, the other side has it's a secondary carbon and a tertiary carbon. So the Grignard reagent tend to attack the R group, or the R minus group tend to attack, and here it is the phenyl group. It tends to attack the less crowded carbon. It tends to attack the less crowded carbon. So therefore, what you will have is a benzene ring and the methyl group on one side, and the other carbon will have the CH3, CH2, CH3, and the OH. All right, so this will be your product. Okay, let me erase the ink so that you can read the formal answer. So once again, guys, the addition of Grignard reagent takes place at the less substituted epoxide carbon. So you should always add the Grignard R group to the less to the less crowded carbon. All right, to the less crowded carbon. With that, I'm going to conclude this video. Okay, please remember to complete your quizzes and then try to do more examples and understand this concept better. Okay, all right, you guys have a good one, guys. Thank you.